I welcome you all in this lecture on dynamic response of second order system. So, last lecture which we saw was on the dynamic response of the first order system, and we took the example of say a hydraulic tank discharge from a hydraulic tank. Okay. In this lecture we will be talking about dynamic response of second order system, and there are in fact many more examples of this system. If we talk about mechanical system, then the spring mass damper system are one of the popular example of the second order system. Then we can have example of torsional system, or if we go for say electrical circuit, then RLC circuit is again a good example of the second order system, of course, which is an equivalent of the spring mass damper system as we have already seen. So, the second order system will have the terms like d square x by dt square. Okay. So, this is the way to identify the order of the system. Okay. So, the second order system will have this term, and of course, many second order system can consist of an inertia, a compliant and a damping. Okay. So, if we talk about mechanical system, mechanical translatory system, then say we have a mass, a spring and we have a damper. Okay. And if I talk about say electrical system, then we have a inductance, a capacitance and a resistance. Okay. So, this way we can take the analogies among the different systems. So, the examples as I explained to you, spring mass damper system, torsional system in mechanical system and RLC circuit in electrical system. Let us take the example of the second order system. Okay. So, we have say a spring mass damper system. Okay. This spring has stiffness K, the mass has a mass of say m, and damping coefficient of the damper is say C, and say there is a force F being applied here, and there is a displacement x of this system. So, here the input is F, that is the force which is being applied on the mass, and the output is x for this spring mass damper system. Okay. Now, the relationship or the dynamic equation basically will have the relationship between the input force F and the output of a displacement x. So, but you can see this equation, the derivation of this equation we have already seen in mechanical system. In this lecture, as I told you, we are interested in looking at the response of the system, response of this second order system. So, if I take the draw the free body diagram of this system, that is represent all the forces here, say the spring force and damping force, okay, and write the unbalanced forces and equate that to the mass into acceleration. This is what term we are going to get. Okay. So, here this is the inertial force basically, this is the damping force, and this is the spring force, and this is the input force which is being applied. Alright. So, this equation here you can see that x are the outputs and f is the input. Okay. Now, here the variation of x with time depends on the amount of damping present in the system. Okay. As we have seen, we have the damping term also coming here. If force is applied as step input, then if no damping is present, then mass will freely oscillate, okay, and the damping causes oscillations to die away until steady displacement of the mass is obtained. okay, and if damping is high, there will be no oscillation, which means that displacement of mass will slowly increase with time and move towards a steady displacement position. These things, these type of behavior we have seen earlier. Okay. So, here is the plot. So, for this second order system, when it is subjected to a step input, say the force F. So, if I plot the output, that is x versus time, then if there is no damping, then you can see that there are going to be oscillations here, and if there is some damping present, then initially there will be some transients, and then after some time we will have the steady state value, and if high damping is there, then these oscillations will be very small, or almost it will not be there. The values will be gradually increasing and reaching to the steady state value. So, this is how the system behaves with damping. So, let us see the second order differential equation with no damping, alright. So, again here I am going to consider the case of free vibration. So, I am assuming this F to be equal to 0, and since I am assuming there is no damping, so I can make this C term also equal to 0, and whatever resulting equation will be m d square x by dt square plus kx is equal to 0. Okay. Now, let us assume that the solution for this is like this: x is equal to a sin omega n t, where a is the amplitude of oscillation and omega n be the angular frequency of the free undamped oscillations. Okay. Then this equation x is equal to a sin omega n t, if I take its first derivative, then this is dx by dt is a omega n cos omega n t, and the second derivative will be d square x by dt square is minus a omega n square sin omega n t. Now, here you see that this a sin omega n t is x itself. So, a sin omega n t, I can put that as x itself. So, here I have minus omega n square x as this one, okay, or I can write the equation d square x by dt square plus omega n square x is equal to 0. So, here what I have done basically is that I have derived the system equation from the assumed solution of the expression. Okay. So, this is my derived equation from the assumed solution. Now, in absence of C and F, the system equation, as I said, it is going to be m d square x by dt square plus kx is equal to 0, alright. Now, if I make a say write this in this form, I take this m to the denominator here. So, we have d square x by dt square plus k by m into x is equal to 0, and if I compare these two equations, then you can see omega n square is equal to k by m. So, this and this term can be compared. So, we have omega n square by is equal to k by m. So, my solution which was x a sin omega n t, now that solution will become a sin under root k by m t, and this is going to be the solution of differential equation for the free undamped vibration case. Okay. Now, let us consider the case of second order differential equation with damping. So, the previous case was there was no damping and we considered the free vibration. Now, I am going to consider the force vibration with damping. Okay. So, the motion of the mass can be described by this equation. Here you can see that this F is the input force and of course, damping is present. So, we have this term C dx by dt is there. Okay. Now, let the solution consist of transient response and the force response. Okay. Transient means I am calling it at natural response. Okay. So, I am using here the subscript xn. Okay. So, the total response of the system is composed of the transient response or natural response xn and the force response xf. Okay. So, let us substitute this x is equal to xn plus xf in this equation, then this is what we get: m d square by dt square of xn plus xf, c d by dt xn plus xf plus k xn plus xf is equal to f. Okay. Now, let us play with this equation a little. Okay. We segregate the terms related with xn, okay, that is the natural response or the transient response, and segregate the term related with xf, that is the force response. Okay. So, we have from here we can look at it, this is what we get. Okay, m d square xn by dt square plus c dxn by dt plus k xn, this part here, and m d square xf by dt square plus c xf d xf by dt from here plus k xf is equal to f. Okay. So, now you can see that we have basically two parts of this equation and this is equal to f. Now, if I assume that this is equal to 0, okay, because I know the natural response, the external the input force is 0. So, let us assume that this is equal to 0, then we must have this part equal to f. Okay. So, now let us see the solution of the transient equation, that is we are going to look at the solution for this part and then we will look at the solution for this part and then we will sum up the solution and we will get the general solution. So, let us take the first part, the solution of transient equation. So, this is my transient equation, m d square xn by dt square plus c dxn by dt plus k xn is equal to 0. Okay. And let us assume the solution for this to be xn is a e to the power st, where this a and s are constant. Now, if this is solution of this equation, then we can substitute this in this equation. Okay. And of course, as you know, here there is a differentiation 2 times and here is differentiation 1 times. So, when we do that, this is what we get. Okay. S square term I am getting here because there is twice differentiation, and s term I am getting here because there is once differentiation, and here we are substituting as it is. Now, if I take this a e to the power st term outside, then this is what we have. Now, you see this into this product is going to be 0. So, either one of them has to be 0. This term cannot be equal to 0 because we have already assumed this as equal to xn, and if we take this term to be equal to 0, then what will happen, that our transient response itself will become 0. So, I do not want to take this term is equal to 0. So, this means that this term will be equal to 0. So, this equation ms square plus cs plus k is equal to 0 is very popularly known as the auxiliary equation. Okay. And you can see that this is a quadratic equation, and I can write the solution for this quadratic equation as s is equal to minus c plus minus under root c square minus 4 m k upon 2 m. Okay. And we can take these two terms here with c, as well as I can take this 2 m term here inside. So, I can write it like this, minus c by 2 m plus minus under root this whole square minus k by m. And now, here what I do basically, I write this first term in terms of k as a coefficient of k by m. So, this is my c square as it is, this is my 4 m is square. So, m I am distributing, so 4m and m here, and I am multiplying a k and dividing by k, so that this value does not change. So, this is how I have written it, minus k by m is this one. Now, as we have seen, this k by m can be written as omega n square, okay. And if we define, say, zeta square is equal to c square by 4 m k for this term, then zeta I can write as c by 2 under root m k, okay. So, as I said, solution for s in terms of omega n and zeta is given by this equation, that is minus zeta omega n plus minus omega n under root zeta square minus 1. Now, you can see here the solution for s is going to depend on the value of zeta, which is popularly called as damping ratio in the vibration terminology, okay. So, here if zeta is going to be more than 1, then naturally we are going to have the two different real roots, because this number inside here is going to be a real number, okay, more than 1. So, this we are going to have the two different real roots, and I can write those real roots as S1 and S2 minus zeta omega n. One value will be positive here and the other value will be negative here, okay. So, once I have the values of S1 and S2, I can write the general solution as xn is equal to a e to the power S1 t plus b e to the power S2 t, okay. And since here we are assuming zeta to be more than 1 or damping ratio to be more than 1, this type of system is said to be over damped, okay. Now, we can have another case when zeta is equal to 1. So, if zeta is equal to 1 here in this equation, then you see that this term is going to be equal to 0. So, you are going to have the two equal roots of minus omega n, because I am substituting zeta is equal to 1 there, okay. So, in case of two equal roots, I can write the solution xn as at plus b into exponential e to the power minus omega n t, okay. And this case, that is of zeta is equal to 1, is said to be critical damped, okay. Now, let us see the third case, that is if zeta is less than 1. So, here if this zeta is less than 1, then you see that what happens, this term becomes a negative term and the square root of negative is going to be a complex number, okay. So, we are going to write that thing in a little slight different way, that is I am going to write 1 minus zeta is square, okay, and whatever negative term square root is coming, that I am going to write as j, okay. So, s will be minus zeta omega n plus minus j omega n under root 1 minus zeta square, and here this zeta is always less than 1, okay. So, if this zeta is less than 1, this number will be a positive number, but of course, that negative sign we have already taken care by introducing j here, okay, fine. So, this is my general solution. Now, let us define a term omega d here which is equal to omega n into under root 1 minus zeta square, okay. So, if we do that, this is what my solution is, s value of s is going to be minus eta omega n plus minus j omega d. So, I can write the general solution if I substitute for the values of S1 and S2 here. So, this is a e to the power S1 t plus b e to the power S2 t. So, I have substituted values of S1 and S2 here in terms of omega n and omega d, alright. Now, I can split these terms, that is this term first term of exponential of this one and first term of exponential of this one. So, these two terms can be split up and I can take this exponential term outside. So, this is what I am left with, a e to the power j omega dt plus b e to the power minus j omega dt. And we know that here this e to the power j omega dt I can write in terms of the cosine and sine terms. Okay. So, cos omega dt plus j sin omega dt, likewise I can write for minus of this one like this. Okay. Now, if I substitute these two exponential terms here, okay, this is what I am going to get. Okay. So, we will have this same term over here and here I am going to get a plus b cos omega dt plus j a minus b sin omega dt. Okay. Now, this a plus b I can write as another constant p here and a minus b I can write as another constant q, and this way I get an expression for x n. Okay. So, this x n is this one, okay, and this represents damped oscillation with exponentially decaying amplitude. Okay. You can see here this is amplitude is exponentially decaying, and this term omega d is equal to omega n 1 minus zeta square is called frequency of damped oscillations. Okay. So, now let us see, so these three cases were for the transient cases. Okay. Now, let us see the solution for forcing equation. Okay. Now, for forcing equation I can assume because in this case there is going to be an input. Okay. So, I can assume say let there be a step input of size f at time t is equal to 0, okay, and I assume the solution as xf is equal to a, where a is a constant. Okay. So, if I take xf is equal to a and I substitute it here, these two terms are going to be equal to 0. So, what I will have is Ka is equal to f, and from here I can find out A as f by k, and this is going to be my solution. So, xf is equal to f by k is my solution for forcing equation. So, the complete solution can be written as summation of the transient part and the forcing part. Okay. So, now let us write the complete solution for all the three cases, that is the overdamped case when zeta is greater than 1. So, we have this part is the transient part and this part is the forcing part. Okay. Similarly, for critically damped case we have this solution as we have seen is for the transient part, or this is for the forcing part, and similarly for the underdamped case this solution is for the transient one and this is for the forcing one. Okay. And now by seeing these three equations 1, 2 and 3, that is equation for overdamped case, critically damped case and underdamped case, we can see that when t tends to infinity here, okay, all these terms tends to become 0. Okay. These terms will be decaying to 0, and this will be leading to a steady state value of x is equal to f by k, and of course, which is the steady state solution. Thus, we can write a general form of the second order differential equation, and this could be like this: a2 d square x by dt square plus a1 dx by dt plus a0 x is equal to b0 y, okay, where y is the input and x is the output. Remember the case which we have seen, it was m d square x by dt square plus c dx by dt plus kx is equal to b is equal to f. Okay. And for this case we can write omega n square as a0 by a2 and zeta square as a1 square by 4 a2 a0. So, this is the general expression. If we remember this, it will help us in treating the systems, second order system which are there from the other energy domains as well. So, if I plot this behavior, then you can see that this is going to be the over damped case, okay. This is going to be the critically damped case, and this is going to be the under damped case, and see this F by K is our steady state value, okay, which corresponds to the force response, which corresponds to the force input, fine here. Now, as I said, we can use the same concept of seeing the response of a second order system in many different system models, okay. For example, if I take this RLC circuit and suppose if I am giving some step input here, and if I want to know the behavior of this system, that is either in terms of what current is going to be there through the circuit, or if I want to know that say how the voltage will be getting built up across the capacitor, all that analysis I can carry out similar to one which we have seen previously. Similarly, we can analyze a torsional system also, okay. So, we can have say a disc with a shaft here, okay, and suppose if certain torque is being applied here, okay, then we can have the opposing frictional torque and the opposing torsional torque here, okay, which actually corresponds to the damping, torsional damping, and which corresponds to the torsional stiffness of the shaft, okay. And then we can analyze, we can write the system equation, and we can analyze the system in the similar way as we have seen. Here is another practical example for this, the strip chart recording. Here you can see that there is a fixed rigid support and there is a pole here through which spring is mounted. There is a mass here which is being supported on say bearing, and there is a pen paper contact, okay, and so there is a force being applied in this direction, okay. So, this example we can write the system equation for this case. Also this expression for this case is going to be similar to what we have seen in the simple spring mass damper system, okay, and we can analyze the behavior of the system in a similar manner. So, if you want to further read this, you can refer to as I have been telling you W. Bolton Mechatronics by Pearson Education. Then we have our book Intelligent Mechatronics System, and another Introduction to Mechatronics and Measurement System by Histon and Alciato, where you will get ample amount of study material to consolidate your fundamentals further. Thank you.